We'll keep our study on lecture 10. So on Tuesday this week, we actually studied something about the Lewis structure, and we we studied how to draw the Lewis structure of a simple atom, how to draw the Lewis structure of a molecule, and especially how do we differentiate the Lewis structure between a molecular compound and a ionic compound. So there are actually something remain for this chapter, which is about the electronegativity and polarity. So actually, so this all begins with the phenomena we actually see in our daily life. Why the oil and water don't mix. So basically here I'm showing you a glass of water and with some oil floating on its surface. If you combine the oil and water in the container and they separate into two distinct regions, have you ever think about the reason behind this phenomena? So actually, this is because this can be well explained by the electronegativity rule and the polarity theory. We're just gonna study. Okay, so now let's first think about the Lewis structure of a water molecule, which is H2O. So now, as you can see here, um, there are actually two bonds between the oxygen and hydrogen, and each bond consists of an electron pair, and these two electrons share between the oxygen and atom, between the oxygen atom and the hydrogen atom. So now let me draw a Lewis structure of this water molecule. So we have water, and so this is a Lewis structure of a water molecule. So we have two bonds, and this oxygen molecule have two lone pairs, and this two bond we call it the covalent bond. So as we mentioned on our Tuesday, the covalent bond are something or are the result of two atoms are sharing electrons, right? Are sharing electrons. And for the ionic bond, it is because of the electron transfer. For covalent bond, it's because of the electron sharing. Uh, but actually, the oxygen and hydrogen atom each donate just one electron to this electron pair, but they don't share them equally. So actually, oxygen atom takes more than its fair share of the electron pair, which means actually um, this oxygen actually is stronger compared with the hydrogen. So this two electron within this OH bound are closer to the oxygen compared to the hydrogen atom. You can think about if I am like I'm trying to like pull a rope with a very strong person, for example, Dwayne Johnson, The Rock. He's definitely more stronger than me, so he can actually drag the rope more closer to him. So that is exactly what is happening now. So actually, the oxygen atom have a stronger ability to drag the electron to itself compared to the hydrogen atom. So as a result, although we said, okay, this oxygen and hydrogen bond is a covalent bond, they they share the electron, but these two electrons are not shared equally by these two atoms. So we we use a new word here. We use a new terminology called electronegativity to to determine the ability of an electron the ability of an element to attract the electron within a covalent bond. So as by this definition, it actually try to define how strong an atom can drag the electron to itself. So oxygen have more or have a higher electronegativity than the hydrogen, which means on average, the shared electrons are more likely to be found near the oxygen atom than near hydrogen atom. So if you see this picture actually clearly shows all of the electrons are actually more closer to the oxygen compared to the hydrogen. But just for your information, this little dot doesn't really represent a single electron. So we call this like an electron cloud. So this single dots actually just represents the possibility we can find the electron near certain places. Whenever you see more dots or an area with higher density of this dot, it means this certain area have the higher possibility that we can find the electron. So from this picture, you can see oxygen definitely, we have definitely a higher possibility to find the electron around the oxygen compared to around the hydrogen. So oxygen have a higher electronegativity or have a higher attraction to the electron to self. So since electrons are carrying the negative charges, since electrons are carrying negative charges, as a result, because oxygen are extracting more electron to itself, so oxygen will carry relatively higher amount of the negative charge surrounding it. Comparably, for the hydrogen atom, it will have relatively a lower density of the negative electron surrounding it. So we use this two symbol, the delta plus and delta minus, to represent the relative value of the electron density surrounding an element. So uh, because oxygen have a relatively a higher electron density, so we give it a delta minus, and for the hydrogen we give it a delta plus. And as a result of this uneven electron sharing, we call a dipole moment will be formed between these two between this OH bound. If you see here, because now let me draw a OH bound. Because for the oxygen, it carries relatively a higher value of the negative electron surrounding it, and hydrogen contains relatively lower density of the electron surrounding it. There will be a dipole formed. So we use a arrow to represent the dipole moment of the electron, something like this. So this represents the dipole moment. We gave it the name of dipole moment. Okay. All right. So for the polar covalent bond, the covalent bonds that have a dipole moment are called the polar covalent bond. What does that mean? The polar covalent bond means the two electrons within the bond are not equally shared between the two elements. Okay? And the magnitude of this dipole moment and the polarity of this bond really depends on the negativity difference between two elements within the bond and the length of the bond. So we actually give it a scale to measure the electronegativity. So the value of the electronegativity actually assigned using a relative scale on which the fluorine, we actually define the fluorine have the most electronegativity element. So we give the fluorine as a scale of 0.4. Okay, so fluorine is the one that have the highest negativity, so we give it a 4. So other elements are just a comparable value compared to this fluorine. Now from this one, you can see, okay, we have the highest one for the fluorine, which is on 7A group, and we have the lowest one, which is the cesium, which is only 0.7 on 1A group. So this is actually a periodic table, as you can hear. So we can actually observe a pretty strong trend in this periodic table. So basically, the trend is from the lower right to the higher left. The electron negativity of the element are gradually increasing, which means the ability for the ability to drag the electron to itself are gradually increasing. Okay, this is about the electron negativity scales of the element within this periodic table. So uh, so now probably you'll be curious. So what if we have exactly two elements have the exactly identical electronegativity? So for that case, for example, for all the like the diatomic molecules, for example, as a chlorine or oxygen or hydrogen, chlorine, oxygen, nitrogen, or hydrogen. So these molecules are all the diatomic molecules with exactly the same atoms forming a bond. So within this bound, because they're the same element, so their electronegativity for this element are exactly the same, which means in these scenarios, the electrons are completely equally shared. So we give this bound a name called the non-polar bound, or non-polar covalent bound. Okay. So if there's a large electronegativity between two elements, for example, like the sodium chloride or cesium fluorine, you'll find, okay, uh, because their electronegativity are so different, which means the electronegativity for the fluorine or the chlorine are much larger than that for the sodium or for the cesium. So because the difference are so large, which means their electrons are actually completely dragged from the element with lower electronegativity to the element with higher electronegativity. The electrons are completely transferred, and as a result, because the electrons are completely transferred, we got a positive ion, which means the electrons are completely lost and gained by the negative or by the halogen element. Cesium is the same thing. Cesium's electrons are completely lost because the electronegativity of the fluorine are much larger than that for the cesium. So they will form a ionic bond. Okay, in this case, they are the ionic bond. So the middle example between these two extreme example are we have some molecule with relatively different electronegativity, but their difference are not that large. So the electron from the elements uh, with low electronegativity are not completely lost, but they are just largely robbed by the element have the higher electronegativity. An example is hydrogen fluoride. Okay, hydrogen fluoride. So the the electron for the hydrogen are not completely lost. So but they are just largely transferred from the hydrogen to the fluorine. So in this case, we give it a name as the polar bound or a polar covalent bound. Okay, polar covalent bound. So now, as you can see here, we have three type of bound. Covalent bound can be classified into two categories. One is in nonpolar, another one is polar. Okay, and we also have a ionic bound. So now you can see the electronegativity are actually the real root cause for the real root cause why we have this different bound. It's all because of this electronegativity difference. So whenever the electronegativity between two elements are within zero point 0 to 0.4, we tend to believe this type of bound are called the nonpolar covalent bound. Okay, but whenever the electronegativity whenever the electronegativity difference between the two elements are within zero point 0.4 to 2.0, we tend to give it a name as a polar covalent bound. For ionic bound actually you can also think about the ionic bound. It's just a bound. So the only difference between the ionic bound and covalent bound is the element that are forming the bound have a huge difference in their electronegativity. So whenever the two elements have the electronegativity difference within zero point 0.2 to 3.3, we tend to believe this bound are ionic bound. Now let's study a new concept called the polar bound and the polar molecule. Okay. First, let's try to see this question. So does the presence of one or more polar bonds in the molecule always result in a polar molecule? So the answer is no. So why the case? So so now we should first understand what's the definition of the polar molecule. So a polar molecule is a one with definitely with a polar bound that add together. So this polar bond does not cancel each other to form a net dipole moment. For example, now let's see some see some typical examples. We'll first go to our most classic example of the carbon dioxide. Okay, we'll use this carbon dioxide as an example to see why the carbon dioxide is a non-polar molecule. So here is actually a simplified structure of the carbon dioxide. On Tuesday, we learned that carbon dioxide is a completely linear structure. So all of these three elements are on the same line. Okay, or it is a linear structure. We know since this carbon and oxygen are the different type of element, and their electron negativity difference is 0.1. Sorry, it's 1, 0. So their electron negativity difference is 1.0, which means this carbon and oxygen bound, it is definitely a polar bound. So in this carbon dioxide molecule, we have two polar bound. One polar bound is actually pointing, the dipole moment is pointing to the right direction, and one polar bound is pointing to the left direction. So we know it has two polar bound. Okay, so does this two polar bound necessarily means this carbon dioxide is a polar molecule? Surely this carbon dioxide is not a polar molecule. The reason is because these two polar bonds are actually pointing to exactly the different position, and these two polar bonds are eventually cancelled. These two polar bonds are essentially cancelled, which means although this carbon dioxide have two polar bonds, but since this two polar bond dipole moment eventually got cancelled, this whole molecule as a whole have no have no dipole moment. So it is a non-polar molecule. Non-polar molecule. Let's see another another classic example, which is a water. We know for the water, the water is a V shape, okay? The water is a V shape structure. It is not a linear, it's a V shape. So the difference between the electronegativity difference between this oxygen and hydrogen bound is 0.4, which means, okay, for this OH bound, it is definitely a polar bound. So if we draw the dipole moment of this polar bound, it will be something like this, okay? So this water molecule have two polar bonds and have the dipole moment pointing to two different two different directions. One is pointing to the upper left, one is pointing to the upper right. Okay, now let's see. This two dipole bond could not be canceled because if you try to add these two bound together, eventually the net result of this two bound will be something pointing to the up, right? So because this two polar bond could not be canceled, two polar bond cannot be canceled. So this water molecule will be a polar molecule. Okay. Now, so this is actually how we define or how we determine whether a molecule is a polar or non-polar. So first we need to make sure there are polar bound within this molecule. If all of the bound within the molecule are non-polar, then this this molecule will definitely be a non-polar molecule. However, if the molecule have certain polar bound, that does not necessarily mean this molecule is a polar molecule, because in some cases, this polar or this dipole moment within different polar bound can be cancelled if those dipole moment are pointing to the different exactly the same scale but pointing to exactly the different directions. Okay, so this is actually a common way how do we define or how we find out whether a molecule is a polar molecule or non-polar molecule. First, if we have two identical polar bound pointing to the opposite direction, it will cancel. So the molecule will be a non-polar molecule. And also, for this case, if the three identical polar bound have the 120-degree and that their dipole moment will also be cancelled. However, if this three dipole moment is a trigonal pyramid arrangement, for example, like the ammonia gas, in this case, their dipole moment will not be cancelled, so this molecule is a polar. For another case, if the molecule is a V shape, such as water, the dipole moment will not be cancelled, so that is a polar molecule. For the last example, like the methane molecule HCH4, this four identical polar bound in the tetrahedral arrangement will eventually cancel. So for the CH4, although it has four polar bound, but overall this four polar bound will be cancelled. So the CH4 is not a polar molecule; it's a non-polar molecule. Okay. So since we actually studied after we introduced you the electronegativity and polarity, now we can try to understand why the oil and water doesn't mix. So water molecule are polar. That is what we learned. But the molecule composed of the oil are generally nonpolar. So um, chemists actually define a rule called the like dissolve like. So this rule actually states the polar molecule interacts strongly with another polar molecule because the positive end of one molecule is actually attracted to the negative end of another, just like the south pole of the magnet is attracted to the north pole of another magnet. A mixture of the polar and non-polar molecule is similar to the mixture of the small magnet and non-magnetic particles. So the magnetic particles just attracted together and excluding those non-magnetic magnetics and separating into two different regions. And in the chemistry world, it is like they are separating into two different phases. So that is actually the reason why the polar water molecule attracts to each other, forming a region, and while the non-polar oil molecule are attracted to each other and forming another region, and these two regions does not mix. Okay, this is the scientific explanation of why oil and water don't mix. So here is the end of our lecture 10, and thank you.